Today, I will be rambling about the life history and nutrition of the long-tailed duck, or as Linnaeus would call it, Animalia, Chordata, Aves, Anseriformes, Anatidae, Clangula, hyemalis. Long-tailed ducks are a migratory Arctic diving duck species with distinctive plumage. The species is named for the long pointed tail feathers of the adult males. The long-tailed duck previously had a highly derogatory and racist common name, which ecologists strangely couldn't bring themselves to change until the year 2000. Although the species exhibits strong sexual dimorphism, both sexes display a color scheme dominated by contrasting light and dark areas. Both males and females exhibit a darker color scheme during breeding in the summer, letters G and H here, and during their immature stages, letters A, B, D, and E. The winter head plumage for adult males and females respectively are represented by letters C and F. Long-tailed ducks are full migrants. They occupy the far north in the summers and more southerly coastal and Great Lakes areas in the winter, as you can see on this map. During breeding, they occupy grasslands and inland wetlands where they nest close to the water, and they migrate to coastal areas after reproducing, occupying marine neritic habitats during the winter season. Long-tailed duck courtship begins in February, when males will exhibit an incredible variety of highly unique displays to win a mate. In a 1975 report in Ornithological Monographs, Robert Allison reported a multitude of courtship displays, including lateral head shaking, bill tossing, the rear end display, porpoising, wing flapping, body shaking, and parachuting, which is flying as high as 10 meters before falling back to the water with limp wings. Although long-tailed ducks find mates during the winter, breeding doesn't begin until late May, when the first individuals start to trickle into the summer breeding grounds from the wintering areas. The females alone are responsible for choosing a nest site and building a nest, which consists of a hidden small depression lined with leaves and down. Clutches consist of 6 to 10 eggs, and the females alone will incubate the clutch for about a month before the precocial young hatch. Despite the fact that the males put in so much work to win their mates, they abandon them as soon as incubation begins and leave to begin their yearly molt, where they will replace all of their feathers, becoming flightless and rather sad-looking in the process. The females will abandon their young between August and October and themselves go through the yearly molt then. Sadly, as with many other Arctic species, oil drilling, invasive species, pollution, and climate change have harmed the natural populations of the long-tailed duck. According to the ICUN Red List, the species is vulnerable with a decreasing population trend. In 1971, Benson surveyed breeding long-tailed ducks in Iceland, finding that breeding males and females fed primarily on chironomid larvae. And fish eggs became an important part of the diet in mid to late summer. In 1986, Goody and Ankney surveyed long-tailed ducks wintering off the coast of Newfoundland, finding that the most common foods were the blue mussel, northern Lasuna, and Idotea baltica. Seasonal changes in the long-tailed duck diet seem to be more related to migration than seasonal availability. In the winter, the birds are often in marine neritic areas and feed largely on marine mollusks and invertebrates, as reported by Goody and Ankney. In the summer, as reported by Benson, the diet shifts towards invertebrate larvae and fish eggs, which are common to the breeding grounds of the species. No toxins, anti-nutritional factors, or limiting nutrients have been described in the literature for long-tailed ducks, according to my research. I found proximate analysis of 2 common long-tailed duck items in the literature, the blue mussel and herring eggs. Using our Atwater factors, the metabolizable energy of whole blue mussel is 676 kilocalories per kilogram, and the ME of herring eggs is 736.5 kilocalories per kilogram. And here are my calculations. Now with the herring eggs, we have the caveat that carbohydrates were reported by difference only, so the factor used for carbohydrates in the Atwater calculation was not NFE. Long-tailed ducks have a fairly typical avian gastrointestinal layout, and by that I mean incredibly strange. In their foregut they have a blind sac, the crop, to store recently consumed food, a normal acidic stomach called the proventriculus, and a muscular ventriculus or gizzard, or freaky internal chewing organ, as I prefer to call it. Moving on to the hindgut, things are pretty simple, with a looped duodenum and jejunum, and short ileum that junctures with two medium-sized ceca directly ahead of the rectum and cloaca, or common vent. I was able to find a full diagram, actually imagery, for a dabbling duck species called the Gergani. But Ziala provided detailed diagrams in her work of the long-tailed duck proventriculus and ventriculus, as well as the ileum, ceca, and rectum. And if you couldn't already tell, long-tailed ducks are a monogastric species. During feeding, webbed feet and wing movements allow long-tailed ducks to dive as deep as 10 meters to reach the sea or lake floor, before the bill allows selection of small crustaceans, invertebrates, or fish eggs. The tongue also assists in food collection, manipulation, and swallowing. While the tongue of long-tailed ducks hasn't been extensively studied, many avian species who have marine diets have tongue papillae, which aid in propelling food caudally. Salivary glands also aid in swallowing, although they are poorly developed in birds with marine diets, and it's unlikely that the saliva contains any digestive enzymes. Whole food is transported from the pharynx to the crop via the thin-walled, distensible cervical esophagus. Food is stored in the crop before continuing to the proventriculus, or acidic stomach, via the thoracic esophagus. Some sugar digestion has been shown to occur in the avian crop, namely amylolysis and sucrose hydrolysis. After exiting the crop, food is subjected to hydrochloric acid and pepsinogen, which is secreted by glands in the proventriculus epithelium. Pepsinogen is converted to pepsin, and together with the acid, contributes to initial protein breakdown into peptides and amino acids. The digesta continues to the ventriculus, where musculature facilitates mechanical breakdown of food, while a cuticle layer called coilin prevents mechanical damage to the organ. Major carbohydrate digestion begins when food enters the intestine. Amylase, produced by the pancreas and small intestine, facilitates amylose digestion, particularly in the jejunum. Maltase, sucrase, and palatinase facilitate the digestion of other sugars. Lipases and peptidases are also secreted in the intestine for the complete digestion of fats and proteins. And after these digestive steps, absorbable macronutrient units will be absorbed over the entire length of the long-tailed duck intestine. As reported in Chapter 7 of Ecology and Conservation of North American Sea Ducks, the resting metabolic rate, which we'll use as a proxy for basal metabolic rate, of long-tailed ducks was 5.6 watts, which converts to 4.82 kilocalories per hour, or 15.7 kilocalories per day. And here are my calculations. In 1995, Stepniewicz reported a field metabolic rate, which we'll use as a proxy for daily energy expenditure, for wintering long-tailed ducks of 500 kilojoules per day, which converts to 119.5 kilocalories per day. And here are my calculations. Literature became a little more scarce with regard to daily energy expenditure of reproduction for long-tailed ducks. In 1990, Parker and Holm found that in common eiders, which are a diving duck with a similar range and diet to long-tailed ducks, DEE was 5.2 times greater during laying than during incubation. Obviously, incubation involves heat loss, but temperatures in the summer would be warmer and there would be less heat loss than in the wintering ducks researched by Stempniewicz, where we found our DEE value. So if we therefore make the assumption that incubation DEE is equivalent to wintering energy expenditure, then the DEE of reproduction for laying female long-tailed ducks should be 5.2 times 119.5 kilocalories per day, which equals 621.4 kilocalories per day. In 1971, Sugden and Harris reported the energy requirements for growth of lesser scaup, which are a diving duck with a similar diet, body size, and range to long-tailed ducks. For the scaup, net energy of maintenance and gain ranged from 18.9 kilocalories per day in week 1 of their life to 82.1 kilocalories per day in week 12. According to the composition of whole blue mussels reported in the NOAA technical report, they contain 12.3% crude protein, 2.05% lipid, and 0% carbohydrate. That amounts to our previously calculated value of 676.5 kilocalories per kilogram, or 0.6765 kilocalories per gram. Given our resting metabolic rate previously mentioned, this translates to 171 grams of blue mussel required per day to satisfy the energy needs of basal metabolism. Given our daily energy expenditure previously mentioned, we would need 176.6 grams of blue mussel consumed per day to meet daily energy expenditure requirements. And here are my calculations. According to the USDA data, herring eggs contain 9.6% crude protein, 1.93% lipid, and 4.47% carbohydrate. And this converts to our previously mentioned metabolizable energy value of 736.5 kilocalories per kilogram, or 0.7365 kilocalories per gram. Given the resting metabolic rate previously mentioned, this would translate to a requirement of 157.1 grams of herring eggs per day to satisfy the basal metabolism of long-tailed ducks. And given our previously mentioned daily energy expenditure, long-tailed ducks would need to consume 162.3 grams of herring eggs per day to match daily energy expenditure. And here are my calculations. Thank you very much for watching, and I hope you enjoyed it.